case. Okay, so we're gonna spend about 15 minutes on warm up today. So I'm gonna split you into pairs, and then I would like you to, so we solved the questions last time, but I would like to know, like, I would like you to write out your answer, like with all the, so you said words to explain what your answer was. I would like you to write those words on the board. And then we're going to rotate and you can critique, like, what's different about this? What did they explain? Did they get something that your group didn't get? Or are they missing something that your group has? And then you can write notes on each other's submissions. So I've got two of these questions, and so you'll write one for one, one for the other. Sounds good? And then once we're done with that, I've got a question for us to start today. And I have candy. So when you come up to get your markers, also get a piece of candy. All right. Thank you. That was more than 15 minutes, but I think it was needed and hopefully fun. All right. So we've got a question here. How many ways can a group of 30 students be assigned to travel in a minibus, a van, and a car if the minibus holds 18 passengers, the van holds 7, and the car holds 5? Right? So we're going on a field trip. We've got 30 students. So I think the intuitive answer is, like, if we assign the minibus first, let's say we fill that one up first. And so we can go 30, choose 18. So that's the bus. And then if we go to the one that has the next biggest capacity, that's something, choose 7. What's the something? Yeah, so, well, yeah, 30 minus 18. 12, choose 7. And then we have proportioned this perfectly. And so then we have 5, choose 5. So this is the van, this is the car. Cool. Sounds good? All right. So this ends up being 30 factorial over 18 times 12 factorial. What do we do for each combination? Yeah.
You multiply them because they are not functionally disjoint. I don't have a different wording, but
Correct. Yes. Because we want to fit all 30 students into these 3 cars. And we're going to the Exploratorium or something, right? So they're all traveling to this one event. So this is a sequence of choices. So we're multiplying them together. All right, so we've got the 30 choose 18. And then we've got the 12 over 7 factorial and 5 factorial. And then we've got the 5 factorial over 5 factorial and wait, okay. So n factorial over k factorial, which is 5, times n minus k factorial. 5 minus 5, 0. Okay, we can cancel some of this stuff out. So 12 cancels out, 5 cancels out. And so we end up with 30 factorial over 18 factorial times 7 factorial times 5 factorial times the secret 0 factorial, which is just 1, so we can ignore it. I don't know about you, that looks pretty convenient, right? So we went with our original number of 30 students. We've got 18, 7, and 5. 18, 7, and 5. Great. And it turns out we can generalize this. So here, this is my plan for the day. We can generalize this. And so we say that the multinomial coefficient is something that looks like n choose k1, k2, k3, so on and so forth, up to km. I'll center n there a bit. So we have, it's the same n choose whatever format. And just on the bottom, instead of something like n choose k, we just have numbers separated by commas. So for example, this is actually 30 choose 18 and 7 and 5. That's how we write that. And this number is equal to, as we just saw, n factorial over k1 factorial times k2 factorial, so on and so forth, up to km factorial. So we just choose the numbers that are in the commas, find the factorial of them, multiply them all together in the denominator. And this value gives the number of ways of placing n distinguishable objects into m distinguishable groups of sizes k1 to km. So this is the number of ways to place n items into m groups of sizes k1, so on to km. All right, I've got a question for you now. I have a class of 25 students, and I have decided to randomly assign grades. And I'm randomly assigning 7 students get an A, 8 students get a B, 6 students get a C, and 4 students get a D. In how many ways can this be done? Think about it, 30 seconds. All right, turn to your neighbor. Talk it through. What do you do? What'd they do? Is it different?
We're gonna write that a lot. I think there's a like it's that's good. 25 choose 7. That's like that has an 18 on the top of the next number, but because it's like ten. And then it's left over. That'd be like 25 and over choose the other numbers. I thought it was just you want about 25 factorial over 7. More, but I've heard that. I just want to check it out. Yeah, that's a lot too. No, I don't know. Is that equal to?
Yes, I just checked, just to be sure. All right, what is this? Not a trick question.
What's that? 25, choose
25, choose 7.
8, 6, 4.
Yeah, that's it. Which is 25 factorial over 7 factorial times 8 factorial times 6 factorial times 4 factorial. If you would write that out, that's 138.7. No, yeah, I can read numbers. 138,567 ways for me to do this. Okay, if you have a graphing calculator can like do the combinations and permutations. It can also do factorials. I don't know if a scientific calculator can. In any case, I really like in most cases, I do not care what the actual number is. There's ones on that will do this where like I do care about the numbers. In other cases, I don't really. So like if you write it like this, and then if you show me this is the factorial, so like it's 25 factorial over all of these, then we're good. You don't need to multiply all that out, especially because with factorials, things can get really big really, really quickly. All right. Excellent job. I have another question. It is infamous. I have 20 basketball players. And these 20 players arrive at a gym and they want to divide into 4 teams of 5 players each. Want to split into 4 teams of 5 each. No coach. In how many ways can this be done? I'll just say how many ways? 4 teams of 5 each, 20 players. Think about it, 30 seconds. All right, turn to your neighbor, talk about it.
Yeah, like, what do you, of 5, choose 4 now? One is 500. Well, I don't know if it would be functional, I think. No, that wouldn't be, it would break, because then one number's bigger than the other, it would stop. Both sides.
All right. Someone have the answer? Yeah. Yes. Almost. So the book adds there are 20 choose 5, 5, 5, 5 ways to divide the players into 4 labeled teams. So this is assuming so what the book adds, this is like distinguished items into M distinguished groups. And so so this is a matter of the question not being explicit. They're like, this is an implicit assumption that we have made for this question. But if the actual teams do not matter, so if teams aren't distinguishable, we need to remove the number of permutations. And so if that's the case, what do we divide by? How many ways are there to distinguish the teams? 4, because there's 4 teams. So it would be 1 over 4 factorial, which is, that's 24. Questions? Yeah. Okay. All right. Now we'll talk about the multinomial theorem. By the way, it's called multinomial because so nomial means like name. And we'll talk about this because we'll look at the example a plus b plus c cubed. First of all, if we just have like a cubed, that's a monomial. Like mono means 1, nomial is name, and the name is a. A binomial is like a plus b cubed, because a and b, bi is 2. And so there's 2 named things. And so multinomial is, there's a lot of them. So that's why we call it that. And we call it multinomial coefficients because this sort of, remember when we talked about Pascal's triangle, how combinations lets us say, here's how this works for binomial coefficients. We can use the multinomial formulation to tell us if we've got something like this, like more than 2, what are the coefficients when we expand this out? Like what's each term? And so the multinomial theorem, which is theorem 11.7 in the book, is let A1, A2, so on and so forth, up to AM be variables. And so that's like our A, B, C, D, E, F. We just call them all A and give them a subscript number. So instead of A, B, C, it would be A1 plus A2 plus A3. So those are our variables. Here, I'm gonna erase this part. I'll erase this. We'll talk about that later. So those are our variables. And let n be a positive integer. Then we've got our theorem. So we have this whole big long expression, A1 plus A2 plus so on and so forth, plus AM, and we raise this whole multinomial to the power of something. We want to know what that is. this is equal to the sum of, so we have, all right, so like if we actually write out like a plus b plus c to the cubed, we'll get something like, let's see, we write this out. So we get something like a cubed and no b and no c. We'll get a squared with 1b and no c with some number in front of it, right? So the result is we have some, so we've got a, b, and c, and each of those is going to be raised to some power. This is the same if we multiplied like x plus y squared. We've got like x squared and no y for the first term, right? There's some combination of, we got some of one variable, one or multiples or none of the other variable. And so those numbers, so like if we say x plus y squared, we know that is x squared plus 2xy plus y squared. This is secretly x squared y0 plus 2x1 y1 plus x0 y2, right? With me so far? Those numbers are k. And so we're going to have, let's go back to the actual theorem. So this is going to be, wrong color, n choose k1, k2, so on to km. And that's going to be, so we're going to have some number, the coefficient, and then we're going to have the combination of variables raised to some exponent. And so that's a1 to the k1, or not, a2 to the k2. I've run out of room. So on and so forth until am to the km. So the k's are the powers, the exponents. And then the what we call the multinomial coefficient, that's the number that we just learned how to compute. And so what goes down here is the sum of k1 plus k2 plus until km. And this ends up being equal to n. Because if we think about it, if we square x and y, the first term is x squared plus or times y to the 0. We've got a 2 there, that's equal to n. The last term, y has a 2, that's also equal to n, where we've got n here, that's the power that we raised this whole expression to. All right, that's complicated. That's a lot of math. Let's look at an example. So we will look at what is a plus b plus c cubed. Okay, so there's kind of a combinatorics problem inside of our combinatorics problem. If we've got a something, b something, c something, and we want to have numbers up to 3, we have options, right? So this is going to be, how much time do we have left? 15 minutes. I'll write the first few and then leave the rest to the listener. So we've got 3 to choose something. But from experience, we know that the first term is 3, 0, 0. The second term, we can have the first one be 2, the second be 1, the third be 0. So we have 3 choose 2, 1, and 0. The third can be 3 choose something. So that could be 2, and then we can move the 1 to C. C gets the 1 this time. So it's 2, 0, 1. I'll do the fourth one. 3 choose something, A, B, C. So maybe B gets, so that's the combination when we start with A. Then maybe B gets all 3, A and C get 0, so we have 0, 3, and 0. So on and so forth, right? For the homework, you're not going to be asked to do all of this. You'll be given a specific term. So for example, I would like to know what is the coefficient of this is x to the 5th times y squared times z to the 7th in the expansion of 2x minus 3y plus z to the 14th. So we know our n and we know our k's. So n is 14, k1 is 5, k2 is 2, k3 is 7. So we have our pieces, and we want to know what's the coefficient of that. So from experience, we can say 14, choose 5, 2, and 7. That's great. These aren't just like A, B, and C, though. Do we need to do anything? Because these numbers have well, Z has a coefficient of 1. Do we think we need to do anything? The answer is yes, we do have to do something. And so because this comes from like, when we do like 2x plus y squared, we end up having, so that's 2x squared plus 4xy plus y squared, right? So that 2 follows us whenever we talk about the x. So what we need to do in this case is we need to bring those coefficients along. And so we have a 2, but we also need to raise that to the power of n because, wait, I'm wrong. That's not a 2x squared. It's a 4x squared. I can do algebra sometimes because that's secretly a 2 squared. And so we need to raise 2 to the power of n, which is 14. And then we also need to multiply it by the other coefficients of the variables, which is -3, also to the 14. And secretly, we have 1 to the 14th, which is just 1. So we can ignore that. If you were to write that for this question, that would be great. Again, if the numbers are small enough, then maybe you can write them out. Once the numbers get big, I don't really care. Yeah.
$2.5, does the bottom always have to add up to the top, or is it just so happen that it's always been the way?
5 plus 2 plus 7. Yes, so they do, because if we, so like if we look at these terms, 3 plus 0 plus 0 is 3. 2 plus 1 plus 0 is 3. And so this is just a property of multinomials when you expand it out. Other questions? All right, I've got just one more. I want to know how many rearrangements of the word mammal there is. To do this, I'm going to look at how many M's do I have? 1, 2, 3. How many A's do I have? 2. Exactly. And so the number of rearrangements is equal to the number of letters. Choose the repeat 1, repeat 2, and so on. So this is 6, choose 3, 2, and 1. Yeah.
Was there a question on this for the practice exam last time, but for like October or something?
Yes. And it was a question on the exam as well. But for that one, the number of permutations is just the number of letters factorial. So this is a little bit different. All right. Moving this to the end. No. Ah. Okay, good enough. All right, so I've got problems for the last 6, 7 minutes of class. So for number 1, I would expect numbers. Maybe let's do number 11 first. Let's go in your same pairs as earlier. Do number 11 first because it's Halloween today, and then work on the rest. All right, thank you very much. I will give you back, please come to me and I will give you back your exam before you leave and bring your markers back up. Take more candy if you would like. So yeah, take a picture of what you wrote if you haven't already. I do need numbers for number 1. These problems are pretty much all on your homework. You're welcome. Thank you, and I will see you on Monday.